Roberto, for the kind introduction. Thank you, Tushar and Suresh, others, Charles, everybody who has helped put this Congress together. And thank you for inviting me. Luckily, I'm an early morning guy, so this was not any problem for me at all. So I'll be basically, this talk is a bit tongue in cheek. Uh, you have a problem, GaN is a solution. I'd like to just acknowledge my, just a partial list of collaborators. More than 40 people, 50 people have worked on nitrogen polar GaN at UC Santa Barbara. So I can't give them full credit, but I just wanted to know that this is not me, of course. Why can't I move the screen? Hang on. I can, yeah. So why is GaN the preferred technology to serve our needs alongside silicon? Every semiconductor technology has to have has to be high performance. That's a given. Otherwise, you really don't get into the market. But more importantly, it has to be very reliable. And even more important, it has to have a roadmap for lower costs with every generation. And to have a roadmap to low cost, you have to have very wide market penetration. Now, the reason silicon has gotten into RF CMOS is not because RF CMOS is the very big market. It just happens to be something that silicon can also do while serving the big market of digital silicon. So what we have to do is we have to develop a technology that has a broad application space. Otherwise, it won't serve the needs of the microwave community at a price point that we can afford in commercial applications. Gallium nitride, in my mind, more than any other semiconductor, satisfies all these requirements. Photonics applications, LEDs and lasers being one, electronics applications, which is what I'll talk about today very briefly. Then there are new applications coming out, UV in chemical sensors, disinfection, so on and so forth. This is UV LEDs and detectors. Extreme environmental electronics, putting electronics in high temperature regions like jet engines and so on and so forth. And there the wide band gap of the three nitrides actually is a huge advantage. So, I mean, it's a huge market, the biggest market being LEDs at the moment, right? So gallium nitride is a direct band gap material. Basically, it's a material that can emit light, the property of the necessary property of a light emitting material. And it's the basis of actually now it's a $30 billion LED industry, and nobody would have thought that that was possible. Why? Because if you look at the material under a microscope, it looks like it's torn. It looks like one of my T-shirts, right? I mean, and nobody would actually even think that such a material could be a valid electronic or optoelectronic device, but it is. So sometimes you got to take what nature gives you. The other thing is that gallium nitride in the visible spans all the way from the infrared, which is close to indium gallium nitride, all the way up to the visible and beyond. So one material system can cover the full space of visible light. Now, my original talk was about silicon carbide and GaN, and I kind of changed the title a little bit. But when I started doing gallium nitride, the material that was supposed to replace gallium arsenide was silicon carbide. And silicon carbide MESFETs don't exist today in the market. But they were the thing in the 90s, early 90s. And the reason I believe they don't is because it's a niche. It cannot support the associated markets, neither does it have the performance relative to GaN. It's a future-proof semiconductor. If you want to do something, especially in academia and also in industry, you want to have something that doesn't just have a 10-year time span or a 15-year time span. And look at gallium nitride. It's in solid-state lighting. It's an airborne radar, data center power supplies. This particular area is going to boom with AI. Y'all all have, not you all, but a lot of you may have a gallium nitride powered adapter. If it's small and lightweight, it has got GaN inside. Displays here, it fights with OLEDs, organic LEDs. 5G base stations are powered by GaN now. Home energy systems. This is UPS for your house, and of course the EV market, with where all the power conversion is either using silicon carbide, silicon, or GaN. The GaN FET applications are huge. This is the power applications. I'll come to the microwave. In the power applications, you can see just from a color chart, gallium nitride can basically takes a lot of the applications. Silicon carbide and gallium nitride fight in this slightly deeper blue, and silicon carbide IGBTs look at the green. All right. So even in RF power conversion, forget LEDs, gallium nitride has a huge play. Gallium nitride versus silicon carbide. This is for power conversion. A similar metric applies for RF, and that's why silicon carbide lost to gallium nitride, and gallium nitride and silicon are now in the fight for RF solution. So the reason why gallium nitride works is that it has a GaN advantage, and it has familiarity with people who use silicon. So if you look at the spider chart here, what we've seen is that, and this spider chart, you got to be on the outside where you have robustness, system cost, switching performance, simplicity of design, and so on and so forth. And gallium nitride, the green, has a much larger web than silicon carbide. And compared to silicon carbide, you can see GaN outperforms silicon carbide in power conversion. And let me not be incorrect. Silicon carbide dominates GaN in power conversion today. But my mantra is that it's going to be a flip in about a decade. And the reason is that gallium nitride can also do things that were typically not thought possible with gallium nitride. Here's a gallium nitride transistor with a breakdown voltage of 1200 volts, which can now deliver performance very similar to silicon carbide. The message from this part of the talk is very simple. If you have a future-proof semiconductor where the semiconductor not only serves the microwave market, say 5G as an example, but it serves huge markets associated around, which means that the microwave performance to cost ratio will be good. So when gallium nitride comes in two flavors, now the microwave talk, it comes in two flavors, what is called gallium polar GaN and nitrogen polar GaN, okay? And gallium polar GaN, I'll talk about that, the differences in a bit. But first, let's talk about traditional gallium nitride. Traditional gallium nitride looks like a MOSFET. It's aluminum gallium nitride, a wide bandgap material like silicon dioxide, sitting on gallium nitride, a narrower bandgap material, not narrow by any means, but narrower. And so you have like a silicon dioxide system. It looks like a MOSFET, but it's a MOSFET on steroids because the mobility of the electrons in this material is near 2000, and the mobility of electrons in silicon dioxide is 50. So basically what ends up happening is gallium nitride has a unbelievable advantage over other material system, mano a mano, device to device. I'm not talking about when you bring in beamformers, the integrated circuits associated with silicon that makes silicon so attractive. But as a device to device comparison, there's no. Now, gallium nitride has developed over a very long time. 1983, aluminum gallium nitride was first grown by Asif Khan, who's now at University of South Carolina, and who also demonstrated the first AlGaN-GaN system in 1983. In 1996, my group basically made the first microwave power HEMT, and that basically kicked off a huge interest in gallium nitride for power. And so then in 2000, we also made the kilovolt class AlGaN-GaN HEMT. So in 1996, we kicked off this microwave gallium nitride field, and in 2000, the power conversion field. And then I won't go through all this, but in 2005, we proposed that after the development of gallium polar GaN, which is all this, nitrogen polar GaN, a new form of gallium nitride, would be the future. People didn't believe that, and it's taken a long time to develop this. But right now, from 2005 to 2016 was the first time we showed some serious millimeter wave performance, and I'll go through this now. So here's a short history. You know, things look ugly in the beginning until they start looking good. In 1983, this is the work by Asif Khan when he was at Honeywell in those days, and then APA Optics. And you saw that the mobilities, if you look at these numbers, 350, then they became, then the AlGaN GaN heterostructure, again by RC, was 620 was the mobility in those days, and it was 1677. But with the development of technology now, we have 2000 at room temperature. The first GaN transistor was also demonstrated. AlGaN GaN transistor was first demonstrated in 1993 with an with an FT and F max of 11 and 35 gigahertz. So in these days, in the early 90s, we saw that there was some real possibilities, but people were still a little skeptical because gallium arsenide had a big substrate, it had a lot of momentum. Then what we did was, we basically decided to start doing the microwave power applications of gallium nitride. We thought that the only way gallium nitride is going to get any notice is if we went into the power applications, because we could get current and voltage at the same time. And we did our first demonstration by Yifeng Wu. We got 1.1 watt per millimeter, 1996, and that was as good as gallium arsenide production. So our first transistor met gallium arsenide kind of numbers. So that was pretty, in fact, beat it. So that was when we realized we were onto something serious. Okay. But it was, there's a mantra that even DARPA applies, we all know. To adopt a new technology, it must give you something amazing. So 10 times improvement over the incumbent. Otherwise, the incumbent will catch up. And GaN, so far in 1996, has shown a modest power density improvement. Development must be very rapid because people will lose interest otherwise, and the return on investment can be realized quickly, otherwise it just gets dissipated. But we had one big problem to solve, which was dispersion. So what happened is, if you made a DC device and you pulsed it, which we all have to do in microwave application, the current actually collapsed. At DC, it looked really good, an amp per millimeter. When we applied pulses to it, here's the blue, we had lost like more than 50% of the current, and that's not good. And the reason for that always is our traps. Okay, whenever you have problems with devices, the first diagnosis should try to find out where the traps are. So here the problems were surface traps, which actually captured electrons, removed them from the channel, and this is the current carrying electrons. You remove electrons, you remove current. So this was the problem. This was solved by passivation, by putting a layer on top of the AlGaN, which actually mitigated these surface traps. And immediately we went from around 3 watts per millimeter, which is like it's too exciting, with passivation to 10 watts per millimeter. And then, wow, that's interesting. And then we went to field plating technologies to mitigate the electric field. And then we went from 10 to 25 watts per millimeter. And then by multiple field plates and so on and so forth, Cree in those days showed 43 watts per millimeter. Now we're talking, right? Even if you're not going to be able to actually achieve this full number, you're now talking 10, 20, 30 times the incumbent. Worth pursuing, okay? So now, what were the big things that made this happen, right? One was the field plate. Like I said, this was, here's a gate, and then Alessandro Chini and I basically, who's now in, I think he's in Modena, he did this field plate, and then what we ended up doing is you could spread out the electric field, basically get the peak electric field down with a field plate, and then you could basically increase the voltage handling capability of the device. That's huge, because the big advantage of gallium nitride was the big band gap and the therefore higher voltage. You also wanted to get more current. To do that, we did something very interesting. Likun Shan and I and my group basically introduced what's called a thin aluminum nitride layer. This is like just 6 angstrom, okay? 6 angstrom, a lattice constant. It's very, very thin. And what it did was it took the mobility from 1200, 1300 to 2000, just this thin layer, 6 angstrom. And suddenly we got terrific watts per millimeter and efficiencies and so on and so forth. So here the basic idea is, you got to know what the problem is, and the solutions have to be simple like that. And then Higashiwaki in Japan, working with Mimura, had shown some high FT and Fmax results in 2008. And we did a 10.5 watts per minute and 40 gigahertz around that time. So 2008, things started looking good for even KU band. But there are other promising device avenues also in gallium polar. One is the graded channel HEMT. This is being pursued by HRL, Jong Moon and company. We invented this technology of polarization, of grading the channel and giving you a distributed charge at UCSB, working with Devdeep Jena, Yulia Smoshkova, and others. We basically developed this graded polarization. We showed for the first time that just by grading the material, we could get charge because this was a polar material. There was no doping involved. We were getting charge by just grading the material. This was a big deal. Now, the graded channel device has been optimized. And we showed this. We called it a pole FET. Siddharth Rajan, students now professor at Ohio State, showed this pole FET, which was a FET with no doping. Right? And that showed that all this physics was real, and then it has been optimized by HRL. Okay, and they get high linearity and so on and so forth from this. You could also get what's called a buried FET, which is basically you put pillars into many channels. Each channel conducts current, so you can get a lot of current. You can see here 3.7 amps per millimeter. This is work done by Shinohara at Teledyne. And you could get these pillars, you basically pinch the device off, you turn it off from the sides. It's called a bridge FET. People at Northrop Grumman, Josephine Chang and her team have made slick FETs. These are also similar devices, just more highly scaled. So lots of work going on, right? Tremendous amount of research. What we chose to do at Santa Barbara is nitrogen polar. And what we did was just flip the material on the side. So instead of having AlGaN on top of GaN, so if you look down on gallium nitride, you'll see gallium. And just below that, a few angstroms below that is nitrogen. If you flip it, you'll get nitrogen on the top and a few angstrom below that, gallium. So it's like turning, it's not a symmetric system. You turn silicon, you get the same thing. You turn gallium nitride, you get exactly the opposite. It's a huge difference, okay? And in my group, we decided to take this and basically develop a whole new class of device. And there was another thing. Remember, I talked about surfaces, and remember, I put silicon nitride on there to solve the problem. Well, with nitrogen polar GaN, you have a different way of solving the problem, and that is by a GaN cap. Okay, but we needed to do this nitrogen polar GaN. We had to have a target market. It's very important to know why you want to do it from a first insertion point. So we chose, thanks to Paul Mackey and the Navy advising us, choose W-band, because W-band, the problem is you don't get a lot of power density at high frequencies, and efficiency is terrible. So basically, you got to do a lot of power combining. Here are people who have done amazing work at W-band, combined 2 to 10 FET cells, 2 to 32 chips, and so on and so forth. And here you can get, a huge, 7 kilowatt transmitter from Raytheon with a gajillion chips weighing a gajillion kilograms. So we know the problem. The problem is size, weight, cost. So what we decided to do was increase the watts per millimeter, make the thing smaller, and increase efficiency. And we did this, and Emre Axo talked about this yesterday. We did this thing where we flipped the device, and when we flipped the device, we could get this two-dimensional electron gas with very high conductivity, but the beauty about it, we could put a gallium nitride cap on top, so we buried it. Okay, when we buried it, what happens is, because of the polarization charges the electrostatics of the system, it turns out that by doing nothing, just by growing GaN on top, we could increase the number of electrons in this channel. Just by adding some GaN, the electrons in the channel, no doping. Okay? This is just by playing with the polarization physics, you could add charge in the channel. And we could do regrowth to get good contacts. And then we did a gate to get the right aspect ratio to get gain. And so why is this interesting? The interesting part is, even though you remove the gallium nitride cap under the gate to give you the right threshold that you want from the device, the GaN cap remains in the access region. This GaN cap adds to charge in the channel, as shown in the band diagram on the left here. But for us microwave guys, just think of it as resistance. Without the GaN cap, the access sheet resistance goes from 300 ohms per square, and with current, it goes up even higher to 700 ohms per square. That's too high. With a GaN cap, we can be below 250 ohms per square, and there is no current choke in the system when you put a GaN cap. This is a big deal. And you get no dispersion with no passivation. Why? Because the GaN cap itself is the passivation. And you get beautiful looking curves, high current, and no dispersion. Low dispersion. Brand Romantic showed this. So what happens is you get we've got record high performance. Okay, you can see here we can get performance as high as 45. Now we've gotten actually 50% PAE in many devices. I forgot to put that data. These numbers that used to be 45 are now 52% PAE. And MReactSo has a paper recently, there's a paper coming out, which will show that we have broken the 50% power added efficiency at 94 gigahertz while providing power, okay, many watts per millimeter. This is a huge breakthrough. You can see, look at the power density versus power added efficiency. Here are all the gallium normal transistors, nitrogen polar, it just breaks out of it. It gives the whole microwave community a new opportunity. And what's good at 94 is also good at lower frequencies. So here you can see we measured 94 gigahertz at the UCSB passive load pull system. We got 8 watts per millimeter. The same device we took to Maury microwave, and we measured it at 30 gigahertz, and we got 8 watts per millimeter. And the same device we measured at the UCSB passive load pull system, we got 8 watts per millimeter. It's unheard of. It's the first demonstration of a single device operating over all frequencies with the same power density. Of course, the efficiency went up as you went to lower frequencies. So now you can see you have watts per millimeter going up. We have now, from a single device, 712 milliwatts from one device at 94 gigahertz. Single device putting out 712 milliwatts. And with an efficiency, you can see the efficiency numbers, 32%. This is just the beginning. I believe we can get these efficiency numbers higher. I believe that this number that I'm going to show you, which is a 1 watt device. Here is a 1 watt device from a single device at 94 gigahertz. One device putting out 1 watt at 94 gigahertz. I don't know about you guys, but I like this, okay? Because I can do a lot with this. Right now, the efficiencies are at 21%, but I'm 100% convinced that these numbers will go up very fast because we know what the issues are, and we are addressing them. And now the technology is stable. So you can see now associated power added efficiency with output power. Gallium polar devices are sub 500 milliwatts. And this work is over a watt. So I'm coming to the end around 6:30 now, 6:28. So I'd like to just conclude by saying the following, right? I covered a very broad space. So let me just take a minute to bring it all together. I want to re-emphasize, there is no technology that will be accepted by the market if it's not high performance, if it's not reliable, if it doesn't have a roadmap to lower cost with every generation. And this point, can never be met unless you serve a very wide market. These two are inexorably linked. And so I believe that gallium nitride is the technology that actually links the two. And so I thank my brothers and sisters who work on LEDs and lasers because they help me sell gallium nitride for RF because the ecosystem pricing goes down. Lastly, what I'd like to say is that nitrogen polar GaN is really a breakthrough technology which addresses millimeter waves. And remember one thing which is very important. The data that I've shown here before is not only on silicon carbide, but it's on sapphire. Sapphire is a cheap semiconductor. No, cheap substrate. Okay, very cheap. This is the substrate on which LEDs are built. Now we have a microwave technology on a cheap substrate with high performance. Only the sky is the limit. So with that, I appreciate you all paying attention, and I'm happy to take any questions that you may have. Thank you.
Thank you very much for this very nice presentation. So we have some questions from the chat, so I will read a couple of them. The first one says, what is the reason for improved linearity in graded barrier gallium nitride HEMS?
Yeah, this is actually it's the improved linearity in graded GaN barrier HEMS is still under debate. I mean, it's not. Okay, there are two. Let me answer the questions two ways. There is linearity at a spot point at a certain bias, and then there's linearity over a range of biases. Correct. So the graded channel HEMS, what it does is that because you have the graded channel, you can actually take GM3, which is the third order derivative of current GM3, and which is the source of third order linearities, and you can actually zero it out. There are other ways of doing it. I didn't have time to talk about it today, but derivative cancellation of GM is another way, and we are working on that aspect. So there are many ways to solve this GM3 problem, which is the third order linearity, and graded channel is just one way. But we have shown in nitrogen polar GaN that we have also 20 dB OIP 3 by PDC numbers. So hard to say whether graded channel is the solution. It definitely has good linearity, but we've seen good linearity from other methods as well. And linearity, as you know, is a complicated question. It has, and transmit linearity is very different from receive linearity. So, it requires us to actually spend some time drinking tea or beer or something like this to have that conversation.
Okay, so we have another question. Any side effects on putting a gallium nitride cap layer in the sense of cost of increasing the parasitic cap?
Yeah, a good question. No impact on cost because it's just a 40 nanometers of GaN, or 20 nanometers of GaN. There's zero impact on cost. Does the parasitic capacitance go up? Yes, just because of the way our gate sits. It sits on the sidewall of the cap. So yes, indeed, the parasitic capacitance goes up. But the beauty about it is it's not a parasitic capacitance. It is an enhanced capacitance. But what that also allows us to do is get high breakdown because it relieves the electric field. So I don't like to call it a parasitic capacitance. It is an additional capacitance, but it comes with a benefit of higher breakdown voltage. So
okay.
So I think it's answer is yes, but I wouldn't call it parasitic.
Okay, and just the last question: why gallium nitride transistors power gain seems to be lower, though output power is high?
Okay, so the transistor power gain, linear gain being low. So the thing is that right now, what I showed you is like 7 dB linear gain. In the microwave technology letters, we just published a paper which has 9.5 dB, 10.5 dB linear gain at 94 gigahertz. So the power gain is not fundamentally lower. But what we do is we trade off gain for power. So what I'm saying is that if I wanted to make a device which had an F max of 500 gigahertz, i.e. have a gain of about 12 dB at 94 gigahertz, I can do that tomorrow. There's no problem. But that device would not give me power, low dispersion, efficiency, and so on and so forth. So what you have to do is to get power, you have to get a little bit of this capacitance to give me higher voltage. That kills gain a little bit, but not enough to hurt efficiency. I'm getting 50% power added efficiencies with the gain that I have. The key is to have high drain efficiency. Power added efficiency is drain efficiency times 1 minus 1 over G. So you need enough G. 6 dBs is plenty. But what you need is high drain efficiency, and we get that. Yeah.
Okay, so there are more questions, but I think that we are running out of time. So thank you very much again